Okay, so this separation of protons on across the intermitochondrial membrane, that's our battery. That's our energy source for synthesizing ATP. And so a good question to begin with is how much energy do we have, right? How much is there to work with? How much energy does that proton separation, or so-called proton gradient, how much does it store? Well, let's, of course, reach back to the tools we've been working with over the course of the whole semester and think about the energetics of the problem. The first thing we can do is abstract this a little bit. We can say, okay, let's say I've got my intermitochondrial membrane here, right? And I'm going to have just sort of the inside over here on the right and the outside on the left. So this would be intermembrane space over here on the left. And we got some protons over here, right? But we know we got a lot more protons over here on the outside. We'll just illustrate it kind of graphically this way, all right? And the question now is, how much energy do I have to work with? All right, well, we can, once again, we can write this out in principle, sort of abstractly as potentially as an equilibrium. Even though this is not a process that is at equilibrium, we can say, well, we know we've got this difference in proton level on the two sides of the membrane. Let's just say, how much energy would there be if we had a process like this that could formally be described as at equilibrium? So we can write down sort of a model like this. So proton inside, proton outside. We can say, well, you know, in principle, you could imagine an equilibrium constant associated with that if the process was at equilibrium with that distribution of concentrations. How do you figure out the energy? Okay, well, you can look at that straight away and realize, you know, at a minimum, I've probably got two things I need to worry about, right? I've got a difference in chemical species on the two sides of the membrane. All right. I've also got a difference in charge, right? Because the protons are carrying a fixed ionic charge. All right, well, let's deal with the first one first. Let's deal with the chemical uh, sort of component of this uh, energy, right? Well, we know how to deal with that, right? If you think back to the beginning of the course, you think back to talking about our discussion about chemical potential and how chemical potential is related to free energies associated with chemical equilibria. That's easy, right? So we can say, well, the free energy associated with the chemical free energy, or the free energy associated with the difference in chemical concentration of species, which I'm going to call it delta G sub chem, is just equal to what we would do to begin with, minus RT natural log the concentration of protons on the outside divided by the concentration of protons on the inside, right? Everybody remembers that from the way we started solving problems like this. And it turns out that's pretty decent amount of free energy, right? Because the delta pH between the inside and the outside of the intermitochondrial, the matrix and the intermembrane space is in the range of 1 to 1.4, right? Which means the concentration of protons on the outside, right, is in the range of 10 to 50 times that of the concentration of the protons on the inside. So you plug that into that um, equation, and you go through that. That's decent amount of free energy. But we know, like I said, just in principle, sitting there and staring at this problem, we know there's got to be more to it, right? Because we know that in addition to there being this difference between the chemical concentration, the pH, the hydrogen ion concentration, there has to be a difference in charge state because these protons are not neutral, they're charged. So there's more positive charge over here on the outside than there is over here. Okay, so this separation of protons across the intermitochondrial membrane has a charge component, an electrostatic component, right? So the question is, how substantial is it and how much does it contribute to the overall free energy we have to work with in terms of synthesizing ATP? Well, One way to think about that is to measure it, and people can have, and you can measure the essentially the voltage difference across between the inner mitochondrial membrane, the outer mitochondrial membrane, and it turns out that change in voltage is in the range of about 0.17 volts, right? Or say 170 to 200 millivolts. Okay, well, you look at that and you're like, well, yeah, fine. You think about your, standard sort of battery, right? Whatever 5-volt battery or car battery. It's like, so what? Really, 200 millivolts? But think about this. That voltage difference is not across the terminals of, say, a battery that's like 3 inches long or 2 inches long or something like that. You're talking about a 200 millivolt difference across a spatial dimension in the range of 40 angstroms, right? Roughly the width of a biological membrane, which you sort of now would know from Dr. Carr's section of the class, is, in the ballpark of, say, 40 angstroms. And what that means is that difference of 170 to 200 millivolts across a 40 angstrom spatial separation results in a charge density of the electrostatic field across the inner mitochondrial membrane of somewhere in the range of 200 to 400 kilovolts per centimeter, right? That's a lot, right? That is a big old electrostatic field. There is a big electrostatic separation across that relatively small distance, given the amount of charge separation over that small a gap, right? So the idea is that's what we have to work with. We have the chemical separation here, that where it's a driving force that's in principle would want to equalize this difference of concentration. And we have a difference in charge. We have a greater positive over here and a more negative over here that would also want to equalize. So there's a lot to work with. All right, so we've got some idea of the chemical potential here based upon this calculation that we did right here with the difference in proton concentration. How do we incorporate the electrostatic component to this, right? All right, so again, think back to what we talked about redox. Think about this idea of when we sort of constrained a simple system to only allowing electrical work. We kind of have a similar problem here, right? If we constrain temperature, pressure, volume, all those kinds of things, we can think about just the electrical component of what it would take to take one of these protons, right? And then move it, right, across that electrostatic field of, say, 200 kilovolts per centimeter, right? All right, so let's think about that. Well, if you remember, then we could define the electrical work of a system like this as the free energy associated with the electrical component of moving that charge in that electrostatic field as just being equal to the electrical work, right? Because remember from that lecture, we basically constrained things in such a way that the work was, the free energy was equal to the work if we held everything else constant, right? And again, if you remember that lecture, that's also just equal then to minus N, F, Faraday's constant, N was the formal charge, times the electrostatic field potential. And when I first defined this for you, that was sort of the idea of, moving this, say, from some point at infinity to that point X that was equal to that electrostatic field density, right? Okay, but what if we're already in that electrostatic field at some point and we move to another point, right? All right. So essentially, the difference in moving between those two positions, or the difference in moving from a field potential of, say, 1, right, or whatever, some value to another value, right? that would allow us to say, well, in that case, if we're moving from one point in this electrostatic field, a given potential, to another point in the field, we could say that electrical work has to just then be equal to minus NF times the change in potential, right? And that makes some sense because you had those two numbers here, right? And you subtracted them from each other. Each one of them is relative to sort of like a position in infinity where the potential is 0. You subtract the two from each other, you simply get the change in the field potential between those 2 points, right? Okay, and we can like say, well, we can put that standard state number there, right? So that means the amount of electrical work we have to work with is equivalent to what it would take to move a particle of a given formal charge between 2 different points of electrostatic potential at those 2 different points. Okay, well, this is sometimes written in a slightly different way when you're dealing with molecular ions, right? Usually the formal charge is replaced with another number. It gets a different symbol. It's capital Z. It's known as the ionic charge, right, rather than the formal charge, right? Times F, that's again Faraday's constant, times delta, the epsilon, delta epsilon. Now that symbol is the same symbol we were using both for electrostatic field potential in my previous lecture, as well as for standard reduction potential. And that makes some sense because they're the same number. They're both measurements of electrostatic field strength in volts, right? Okay, so now what we want to know is how do we put this all together? What's the overall free energy we have to work with in standard state free energy in terms of moving a proton within both this chemical and electrostatic gradient, right? This is sometimes known, or it gets a name, it's known as the electrochemical potential, because we basically have both a electrostatic and a chemical potential. So you put the two together and you get electrochemical potential, right? And that's simply going to be equal to, pretty simple, the standard state chemical potential free energy plus the standard state electrical free energy, right? Okay, well, that should become pretty obvious because now all we've got to do, right, in principle, is we got to just combine this expression along with this expression. And we know an expression then, or we can write down an expression for the electrochemical potential. And it's simply equal to minus RT log concentration of protons on the outside divided by the concentration of protons on the inside minus ZF delta epsilon naught, right? Pretty cool, pretty straightforward. Now, there are a couple of modifications here that the way you'll normally see this written. One is to take that symbol, because it's used for other things, and change it to something else, because we're specifically talking about a static field, electrostatic field potential across a membrane, right? And that in standard notation gets its own symbol, right? And specifically, it gets the symbol delta psi. I know we've used psis for other things too, like wave functions, but in terms of thinking about electrochemical potential, people tend to use the symbol delta psi for the electrostatic field potential difference across the membrane. So that's one thing, right? This is sometimes, again, be referred to as the membrane potential. It's still in volts, right? It's still an electrostatic field difference, but it's just a different symbol. The other thing we want to do, right, is hydrogen ion concentration. That's related to something fairly straightforward we've talked about before, which is pH. So we can combine these two ideas of change the notation for membrane potential and pH and rewrite this expression in a form that where it's sort of more commonly seen, which would be, we got to convert to log base 10, right? Because that's where pH is, minus 2.3 RT times the pH, right, on the inside, minus the pH on the outside. There's our chemical potential, all right? minus Z F delta psi, right? Which is the change in electrostatic potential in volts across the intermitochondrial membrane, right? This sort of expression now allows us to calculate the free energy of the electrochemical gradient across the intermitochondrial membrane, given a known measurement of pH difference and given a known measurement of the electrostatic field potential. We know how much free energy we have to work with, and you get the numbers and you go through the calculation. What you find out is that the free energy associated with moving one proton from the outside of an energized mitochondrial intermembrane to the inside, so I'll just write proton transport, okay, clear, is equal to minus 21.5 kilojoules per mole, which seems great. I mean, that's pretty good, right? 1 mole of protons gives us, across that electrochemical gradient, 21.5 kilojoules to work with. That's awesome, except for the fact that this reaction, which is ultimately what we're trying to do here, make ATP, that has a free energy requirement under sort of cellular conditions of about positive 40 to 50 kilojoules per mole. So you look at that and you think about that for a second, and that means something. It means we can't make ATP with transport of 1 proton. In fact, we really probably can't make ATP with transport of even 2 protons. To make an ATP molecule, to synthesize an ATP from ADP and inorganic phosphate, we're going to have to transport 3 protons across that electrochemical gradient. And that gives us enough free energy to then turn around and drive the synthesis of ATP from an ADP and inorganic phosphate. It's cool, right? So that means we need basically about 3 protons per ATP synthesized. Well, cool, that tells us something, right? Important, that's cool, right? Just the energetics alone mean that it's gonna have to work out that way. The question now is, how does that happen? How do you do the coupling, right? And the secret to that comes into this massive protein complex. It's essentially what you would call a molecular machine that is going to couple mechanical work to chemistry. And this is sometimes known as complex 5 of the electron transport chain. I usually refer to it as the F1, F0 ATPase, which is how I learned it. And the next video, we're going to start looking at how that machine works.